HVAC 360, episode number 42, Gas Monitoring. Hey, welcome back, everybody, to another episode of HVAC 360. I'm your host, Matt Nelson. This week, we are going to be talking with Scott Bissett. Scott is the Director of Sales and Marketing over at Armstrong Monitoring. Now, the reason I want to talk about gas monitoring is it's something that I've seen all too often happen on jobs where the engineer knows that they need to provide it. They kind of put it on the drawings a little bit, but it's poorly coordinated, and it's often forgotten about in certain aspects. So, there's a large coordination between the mechanical, the electrical, the contractor, getting it right, knowing exactly what to put in, the bells and whistles that literally that need to go on the system. So I wanted to sit down and talk with Scott a little bit to figure out exactly what the differences are to gas monitoring. What do we need to do? And if you don't gas monitoring, if you're not catching on to what I'm saying, if you have, say, a refrigerant leak, is a typical place that we'd see this. So if you had chiller equipment in a mechanical room and there was a refrigerant leak, you'd want gas monitoring there to be able to detect that refrigerant leak so you can start an evacuation sequence. Or if you're in a parking garage and you have, or a loading dock area, and you have cars idling, or you have a lot of buildup of combustion, products of combustion, and you want to be able to ventilate that properly. You want to be able to detect when the level goes too far to be able to activate that ventilation sequence. It's sad to say, but I've seen these drag on until the end. Nobody resolve exactly what needs to be done and what details need to take place before they get this properly implemented. And frankly, will the system work without it? Absolutely. Would somebody die if the system wasn't put in? It's a real possibility. So, it's something that should be taken seriously, even though the building will still work if it's not implemented properly. So, let's talk to Scott and find out a little bit more about gas monitoring. All right, let's cut to the tape. All right, today we are going to be speaking with Scott Bissett, Director, Sales and Marketing over at Armstrong Monitoring. How are you doing this morning, Scott?
I'm doing very well. Yourself, Matt?
I am doing great, thanks. So tell me a little bit about Armstrong Monitoring.
Well, the company itself, we design and manufacture a full line of fixed gas detection systems for both commercial, industrial, and military industry. The company was founded in 1981, so this is our 32nd year in operation. We're based in Ottawa, Ontario, Canada. Company is ISO 9001-2008 registered, and I guess one of the more interesting pieces of info on the company is that we're powered using 100% green electricity.
Excellent. Well, kudos to that. So tell me a little bit about what's the basic anatomy of when you talk about gas monitoring systems? Or let's even how would you kind of define gas monitoring systems?
Well, the easiest way to look at it would be really, I think, three subcomponents. The first being the sensor, which is the piece that actually will detect the gas in air. The transmitter, which will take the signal from the sensor, condition it, normalize it, and then output it either to a control system or other device. And then you'll have the monitor or controller, as they're often also referred to, which provides power to the sensor transmitters. Typically will also provide the relays that are used for interlocking, ventilation, or other auxiliary devices.
Now, typically these kind of systems are going to be powered off of a 120 circuit. They're not going to be battery powered, are they? Or do you have applications like that?
There are a few systems that are available now that do use battery powered systems. Armstrong Monitoring doesn't use those at the moment. Our view is that it's still an emerging technology. We want to have 100% uptime is really our focus, and the best way to do that at this point is using 110 volt power, as you said, and oftentimes in safety critical applications, we'll actually have these systems running on battery backup as well.
Okay, so not just emergency power, but battery backup as well.
Yeah, and when they're really critical applications, either from a process or from a safety standpoint, it's quite frequent to see a 2 to 3 hour battery backup put in place in line with our system.
So is that something that you typically would, in these types of situations where you'd recommend that to the engineer, or is that something that comes prepackaged with your system?
It's something that we usually will let people know that is available. It's not something that we manufacture, so it's something that we can assist with sizing. Oftentimes, the electrical and mechanical contractors can provide these kind of aftermarket pieces at same or better cost than we could. So we simply want to inform our clients that if you're going to go down this path, this is what you need to plan for. We have certainly provided them on occasion, but it's not always the most effective use of a client's money.
Right. So, I mean, what kind of applications? If somebody's a little bit fuzzy and they say gas monitoring, how would you explain what gas monitoring is, or what applications you'd kind of see it in?
Well, from an application perspective, what we're really looking for is toxic, combustible, or other dangerous gases, whether depleting oxygen, in air. We want to ensure the safety of personnel working in a space, and ensuring that we limit the amount of exposure to specific target gases.
So now, obviously, to detect these gases, you can talk about your three components. The sensors being one of them. That's kind of your key component. I mean, if anything fails, the sensor really has to be the one that is kind of at the heart of the whole situation. So, what kind of different sensors do you have in these systems?
Well, there's really four main sensor technologies that we see being used currently in the commercial and industrial gas detection industry. They do vary depending on the application that you're dealing with, but if I was going to really get down to the technology standpoint, it would be electrochemical cells, solid-state sensors, catalytic, Pallister type sensors, and infrared. Between those four, that would cover, I would guess, probably somewhere in the high 90% percentile.
Okay, so now what for each of these chemical sensors, each of these four different types, what would you say are their strengths and weaknesses of the four?
Well, the electrochemical cells we use predominantly for detecting toxic gases. Their strengths are a very high resolution, so we're able to see in a lot of cases very minute levels of gas, even entering into part per billion ranges. They're very specific to the gas that we're targeting. When they do have cross sensitivities, they're generally very well documented. So from a pro standpoint, they're very, very reliable. On the con side, they tend to be a little bit more expensive, and they do have in some cases shorter usable life than some of the other sensor technologies. Solid state sensors were, I guess, the first commercially available vehicle exhaust sensors were solid state, and they really kick-started the whole commercial gas detection industry. They still do have a use. They are long life sensors, relatively inexpensive, and they are very good for general contaminants. So if you don't know exactly what you're looking for, these will pick up a variety of different compounds. Some of the disadvantages with solid state is that the maintenance requirement is a little tricky. There are some workarounds, but to do it properly is a fairly involved process, and the cross sensitivity that's inherent in these sensors can lead to nuisance and false alarms in many applications. The third type of sensor are catalytic Pallister sensors, and these are really exclusively used for combustible gas detection. They're relatively inexpensive, very accurate, and have a life in typically in around 3 to 5 years, depending on the application. Really, from a con standpoint, the only one that I can think of is that they are susceptible to some poisons, which would bring us to infrared. And the infrared sensors have the advantage of really no consumable used during the measuring process. So they have a very stable baseline. And in some cases, calibration almost becomes unnecessary. And we do recommend checking them, but in some cases there's really no drift in the signal over time. Con to that, though, is that they are a little bit more expensive, and in some cases can be 2 to 3 times the cost of other technologies that could be deployed in a similar application.
Now, I guess which one do you find is most common out of all of them?
Well, I think on the whole, electrochemical would be the most common, but it really does depend on the specific application that you're looking at. In vehicle exhaust, from an Armstrong monitoring perspective, we're almost exclusively electrochemical. I know there are still some manufacturers in North America that are still using solid-state sensors for carbon monoxide. From our perspective, it's not the best technology to be using, but they still are available. When we're getting into refrigeration rooms and applications like that, really the industry standard is infrared, and most of the manufacturers that are providing these types of systems do have either non-dispersive infrared or photoacoustic infrared sensors available. I guess combustible gases, you'll find a mix of typically catalytic and infrared sensing.
Now, I guess when you talk about the different makeups of the 3 components, the sensor and the different monitoring components, what when you go from manufacturer to manufacturer, obviously as an engineer you're like, okay, how can I make these all equal? What kind of varies between the manufacturers that you see? I mean, you've kind of pointed out that sometimes they'll use a different type of sensor, whether it be solid state as opposed to electrochemical. Are there other differences, and what would you say those were?
Well, there are a variety of different strategies that are in use by gas detection companies today, ranging from design to maintenance and installation. If I can touch on a few of them, one of the key determining factors that we see is length of warranty. And if I can speak to the Armstrong monitoring side of it, we offer a full 2-year warranty on all of our electronics. Which is usually about double that of our competitors. That is a pretty significant difference between manufacturers. We also focus on ease of installation. We want our equipment to be very easy for the installers to work with, and that's reflected in our design philosophy. Most of our products use commercial off-the-shelf electrical enclosures. So it's enclosures that our installing contractors are familiar with and that they're used to working with. We don't really do much in the way of nice architectural plastics because really the application doesn't demand it, and they're not intended to be pretty. They're intended to be functional. And that's again a philosophy that separates us a little bit from some of our competitors.
So now, I guess when you talk about these sensors, these gas monitors, what are some of the codes that people engineers would be focusing on?
Well, again, this is one of these questions that's got a bunch of different potential answers depending on the application and the jurisdiction. Oftentimes we'll have multiple regulatory considerations to look at and try to work into a system design, ranging from whether a location is defined as hazardous, and then getting into building codes, state and international mechanical codes, and then looking at federal and state exposure limits from bodies like NIOSH, OSHA, and ACGIH. So they all have slightly different exposure limits, and determining which one is the most appropriate for that application can sometimes be a trick. When we're looking at refrigerant applications in the U.S., we're looking at ASHRAE 15 as really the standard to go to for system design.
Now, is that, obviously I think that, when you talk about exposure limits and you're dealing with enclosed, products of combustion and things like that with parking garages or other hazardous areas that it's probably pretty well regulated and mandated by that. Refrigerant is that? I mean, how does that work into the codes? Obviously ASHRAE 15 is a standard, but is it codified in most jurisdictions, or is it just something that is kind of nice to have?
My view on it is that the engineering community as a whole have really embraced that as the engineering best practice. In some cases, it's not always mandated, but it certainly is looked at as being the correct way to do it by most consultants.
Okay, fair enough. Obviously, anybody on construction, safety first. We have to think about the safety of the owners, and it wouldn't be doing our due diligence, I guess, to kind of not put it in, purposefully not put it in.
That's really the standard that people are going to be held to is, what is the risk and what are the available technologies to mitigate that risk? And if you as a consultant have made a decision to not use a commonly available safety or asset protection system, and there is ever an incident, it certainly could be reflected back on the designer.
Oh, absolutely. So now, when the designers look at these gas monitoring systems, what are some of the things that they should be aware of, or they should keep in mind when they're laying it out, or maybe early in the design, some things that they should think about?
One of the things that we really encourage people to do is to take the time to fully understand the application, and when I say that. What I mean is getting a real understanding of what is expected to be taking place in that environment, what gases are expected. In the case of a vehicle exhaust application, what types of vehicles are going to be operating in that space? I can't tell you how many times we've seen CO only or carbon monoxide only detection systems specified in dealerships that are selling diesel vehicles. So the default behavior is vehicle exhaust equals carbon monoxide, but it gets a little bit more complicated than that when you're dealing with mixed vehicles. We also want to encourage people to be looking at potential interference gases. If we can go back to the example of solid-state sensors, they are still in use in parking garages, and it's the worst-case scenario of a nuisance alarm with a solid-state sensor in a parking garage is the fans will start. But when you're looking at a municipal or a service garage where there's things like brake cleaner and paint thinners and carb cleaners and things in the air, that cross-sensitivity can lead to a lot more nuisance alarms and potentially evacuation of personnel. It becomes, you become worried about a cry wolf type of scenario. So having a thorough understanding of what's going to be there will help a consultant make a more informed equipment selection.
Mm-hmm.
There are certainly other considerations, like the size of the space to be monitored. What the mounting heights, what gases are going to be monitored for, and what the appropriate mounting heights are. Zoning of ventilation, whether there are specific output requirements to building automation or other monitoring systems. Things like other auxiliary equipment, really understanding what you want to have happen when there is a elevated gas reading.
Okay. Now, as far as you talk about distance, the area that it can monitor, the location of it, the mounting height. What are each of the sensors, depending on the different technology, is that gonna vary a lot, or is there something that's more of a standard rule of thumb? How would you describe, at least just if you focus on the spacing and the mounting height?
Well, for vehicle exhaust applications, which really are the most common commercial gas sensing application, we advertise about a 7,500 square foot coverage area per sensor head, which translates to about a 50-foot radius. That's a fairly common number in our industry. You'll see some manufacturers as low as 5,000 square feet. You'll see some as high as 10,000 square feet. The reality of today's gas detection industry is that we're for the most part all buying our sensor elements from the same group of companies. So there are 10 to 15 manufacturers of sensor cells in the world, and we're all buying from that same group. So nobody really makes a safer gas detection system, I would say, from a detection threshold standpoint, at least in the commercial space. So if you take that 7,500 square foot rule, you could probably apply it pretty fairly across the industry. Mm-hmm. The catch is that 7,500 square feet counts on a sensor being mounted in the center of a space, so that you can get that 50 feet all the way around. If it's wall mounted, then you cut that in half. What I generally encourage consultants to do is to locate the sensor where they feel it's appropriate, and then draw a 100-foot circle around it to get a sense of where their coverage areas are going to be.
Right. Now, what about mounting height?
Well, mounting height is again one of these topics. There's a little bit of a bone of contention in our industry. With carbon monoxide sensors, we're all generally in agreement that somewhere between 3 to 5 feet in the breathing zone, effectively, is the most appropriate place to be putting carbon monoxide sensors. When we're dealing with NO2 or nitrogen dioxide, there is a fair amount of discrepancies. Some manufacturers are recommending having the sensors mounted at the top of the space, 18 inches from the ceiling, while others are recommending down 18 inches from the floor. The really important determining factor is the relative density of the gas. And NO2 at room temperature is heavier than air, or slightly heavier than air, which means that once it's cooled down, it is going to settle at 2 to 4 feet above finished floor. So our view at Armstrong is that the most appropriate place to measure it is in that 3 to 5 foot space in the breathing zone, which will provide traceability to what somebody in that space is actually being exposed to. That's the standard that a building owner or operator is going to be held to. What did somebody breathe in? And to me, it's most appropriate to measure in that area.
Now, as far as the logic goes, I mean, obviously, I think that the NO or the was it NO2,
Yes.
The diesel exhaust essentially is when you talk about mounting it up high, and I've seen that quite a bit. Mounting up high, it's kind of, I guess, part of the reason is that it may not be at a room temperature because it's going to come out of the exhaust hotter than air. And also, so that would make it lighter than air, and it would also be that if you're dealing with vehicles that may have a top-mounted exhaust, I'm just trying to point out why that would be up high. Is that accurate?
Yeah, and when I came into the industry 10 years ago, that was really the school of thought, and we looked at it and started to see more and more vehicles that have bottom exhaust, whether we're talking about passenger vehicles with the cost of gas now seemingly always increasing. You're starting to see more and more diesel vehicles on the road. Those are coming out of the bottom. We're starting to see more and more municipalities looking to diesel vehicles for their work trucks. So more and more diesel pickup trucks on the road. Whether we're talking about courier delivery vehicles, again, bottom stack exhaust or bottom exiting exhaust. The issue with mounting a sensor up high is that while hot gas does rise, who's to say how high? If you're putting an NO2 sensor up at 30 feet, and you've got a mix of vehicles, some top stacked, some bottom exiting, you may not always catch it up high, but you will catch it in the breathing zone, whether you catch it as it initially rises when it's hot, or if you catch it as it cools down and settles, passing through the breathing zone.
Right. So I guess
there certainly is logic to having it up high, and if you're looking for the most rapid detection when dealing with top exiting, whether it's tractor trailers or buses, there certainly is an argument to be made. But I wouldn't do it at the expense of having one in the breathing zone. My view is that if you're going to do that, it should be in addition to.
Okay, excellent. So, I mean, essentially, you're protecting that breathing zone. So, like you said, whether it's going up or coming down, eventually it's going to pass through the breathing zone, and you want to protect the occupant because safety is your number one concern.
Yeah, and that's really why we're putting these systems in there, is to protect personnel in a space. And so measuring their actual exposure, to me, is the most logical way of ensuring their safety.
Okay. Now, if we obviously switching gears to the other area that it's the primary focus, refrigerant. Spacing and mounting height for refrigerant. What's your take on that?
Well, we recommend having your sensor mounted typically from 6 to 18 inches off the floor, as close to the chiller as we can get. The best rule, in my view, of as far as determining number of sensors, is one per chiller. Now, if you've got several chillers in very close proximity that are all the same refrigerant, there may be an opportunity to cost engineer down a bit and make use of a single sensor. But if I was asked to give just a general rule, I'd count on a sensor per chiller.
Okay. Now, does it matter, if it's a 410A or 132? I mean, as far as different refrigerant types go, you still want it mounted down towards the floor.
For most common commercial refrigerants, yes. The only I guess major exception to that rule would be ammonia. Ammonia tends to evaporate very quickly, and it is lighter than air. So when we're dealing with ammonia chiller plants, whether it's arenas or other applications, we tend to recommend having the sensor up high.
Okay. Now, is that just to make sure I'm clear about this? Does that mean up high in addition to a sensor in the breathing zone?
No. Well, no. This one with ammonia, it's generally going to be. It's rare that we see a slow leak that'll settle in the breathing zone. Like it's going to leak and then it's going to go up. And the risk really isn't so much that somebody's standing over it when it's leaking. Mm-hmm. It's going to pool at the top of the space, and so we want to detect it as it pools.
Okay, so basically, there's no problem about warming up, cooling down, anything like that. If ammonia leak, it's going to go up. And obviously, it's one of those refrigerants that if it starts to leak, you're going to know it pretty soon, because it's
the ammonia. The compound itself is highly aromatic, so it's in many ways your nose is a highly effective gas sensor when we're talking about compounds like ammonia.
Now, I've seen a lot of conflicts with just kind of coordination in general with these gas systems. So, what's your preference? I mean, what if a designer asked you how should I specify one of these systems? Would you say put it in the specs? Would you say put it on the drawings? What are some of the things that designers need to keep in mind when coordinating it with not only maybe architectural or to get the alarms, buzzers in the right locations, or whether it be electrical, getting the power where they need to?
Sure. Well, one of the things that we really like to see, which makes it very clear for us and for our representatives, is a schematic showing power coming to, what fans are being activated by what relays, how many sensors are in a given zone, how many zones are being brought back to the controller. It, to me, is really the best way for an engineer or consultant to communicate what they want this system to look like. In addition to a nice schematic, a floor plan showing not just sensor locations, but how those sensors are intended to be wired is great, because what it allows people to do is to put conduit in the slab prior to construction, which can certainly make things a lot easier. We're starting to see more and more people try not to eliminate the conduit from view. So having an understanding going in of where the wire is to be run will allow those types of systems to be installed very, very clean looking. And really, the other consideration is to consider the maintenance aspect of it. So go in knowing that these systems are going to need to be accessed on occasion, whether it's at a 6-month interval or an annual interval, and to put pieces in place that will allow that activity to take place with a minimal amount of effort. And it's whether it's things like preamps or not having a sensor directly over a vat of biodiesel, as an example. Consider the not just the initial installation, but also the ongoing maintenance of these systems.
Okay. Now, when you talk about the electrical connections, is it pretty much you're going to have a single point power connection to your devices, and that's going to be at your main panel, and the rest of it's low voltage, or what? How is it kind of in general? How is it laid out?
Most systems with remote sensors are going to be your line voltage to your controller, and the controller will provide low voltage power out to the remote sensor heads. There are certainly cases where we'll have transmitters that are really operating on their own, that are pulling low voltage power, whether it's from a control system or other interface. It really does depend on the application.
Now, what about
what I think would be fair to say is that there are a variety of different power options available, and it's something that can be really engineered. You don't have to just take it as it is. Some of our more common standalone products are designed for 110, but we make them in both 24-volt DC and 24-volt AC versions as well.
Okay. So now, I guess you talk about, so it's been detected, say, for instance, your refrigerant's been detected. Now, obviously, you have audible and visual alarms that come into play. So, and
yeah.
I guess I can even lump down, I guess let's focus on those two, because we can go into the breathing apparatus and the, obviously the remote shutdown as well. But are there different stages of alarm?
Well, with the way that ASHRAE 15 is written, there is not a staged alarm. It simply says that you need to alarm both audio visual inside and outside every entrance to the mechanical room when the gas values exceed the time weighted average TLV, which the trick is that for many refrigerants is not established. So there isn't a number that you can look at and say, well, I have to alarm at this level to meet code or to meet ASHRAE 15. What we typically do is we take advantage of the accuracy of the new infrared sensors, and we try to alarm at the lowest reasonable level. The reason behind that is that refrigerant is an expensive product, so we want to catch a leak as early as possible. We want to protect not only the personnel that could potentially be working in the space, but we also want to protect the investment of the building owner or operator, who've got a bunch of money sunk into the refrigerant that's in their chillers.
So, and two, I guess I could point this out. When we talk about alarms, it's going to be mostly on the refrigerant side. Are you alarming the vehicle exhaust or something like that? It's just a fan kicking on.
In many cases, yeah. We typically encourage people to look at what they want to have happen when, and generally speaking, our alarms are done in conjunction with the two established exposure limits. So one will be an 8-hour average exposure, and the other will be a 15-minute short-term exposure limit. So if we look at a parking garage as an example, there's no need on detection of a low alarm of carbon monoxide as an example to turn on alarms and horns and likely panic anybody that could be working in that space. That's a situation where you can simply turn on an exhaust fan, clear the air from the space, and it's business as usual. When you get into that higher level of alarm, there's obviously something going on that's not allowing the ventilation system to clear the buildup quickly enough. And it's a situation where we want people to be aware that there's a potential problem and that they likely will want to leave the area.
So, I mean, I guess would that just be a sound alarm, audible alarm? I mean, what?
We've seen it done a variety of different ways. Our monitors themselves include audible alarms, and certainly are available with strobe type devices as well. We manufacture and provide multiple kind of audio-visual combination devices. We don't see them used terribly frequently in commercial parking type applications, but there are certainly some that will have alarm lights come on when there is a high level detected.
Now, what about I guess one of my examples, if I get back to the chiller entrances, at the entrance to a mechanical room, I guess what are some of the things that you'd expect to see? Audible alarm, a visual alarm, possibly a manual shutdown to be able. Yeah,
by code, we need to have at every entrance we need to have audio and visual alarm. You do need to have not at every entrance, but at likely the main entrance to the mechanical room. You do need to have a shutdown for combustion sources, and you do need to have ventilation interlocks. So you need to have the ability to turn on exhaust fans in that space from outside of the room.
So that's just, is that like an override? Obviously, I think that, the detection would automatically trigger a exhaust, but is there some sort of, secondary exhaust that's required?
It's really a safety, it's really a second level of safety. As you said, everything works as designed. The fan should already be running. There should be, the boiler should already be shut down. But it gives you an opportunity to just absolutely ensure that those two things have happened if there is a refrigerant leak.
Now, what would you talk about when you talk about breathing apparatus? Obviously, I think that that's one of the things that pops into my head when I said, okay, you got the light flashing, you may want to enter the space, but obviously you need to take precautions. So what sort of precautions can we take for protection for, say, anyone going in to try to repair the space? Is that something that you'd want the anybody to be able to don, or do you want to have them to call a technician in, and they should be specially licensed or equipped to handle this, or how would you typically recommend that?
Well, our approach really is to have really two levels of alarm, and the first is a relatively conservative number. It would allow somebody to work in the space without the benefit of breathing apparatus. And that second level is one that while somewhat arbitrarily set, is a level where we've kind of gotten to a point where the leak is getting worse. The ventilation system is not able to clear it as quickly as it's occurring, and we do want people to leave the area at that point. From a breathing apparatus standpoint, it's not. From an Armstrong monitoring perspective, it's not our area of expertise. Mm-hmm. So we generally will defer that to manufacturers who specialize in it. My personal view is that it's not something that we want just anybody running into a room, putting on an SCBA and running into a room to investigate a potential issue. Really, the SCBAs, there is a training requirement for their use, and in many jurisdictions there's a fitment requirement for their use. So really, it should be left to qualified personnel, whether they're on site or whether it's a subcontractor that's coming in to respond to a leak. My recommendation would be to leave the fixing of a potential issue to those who are trained and qualified to do so.
Okay. So I guess it would be safe to say then that, you go and you design your gas monitoring system, but you make sure that the owner, you have that conversation with the owner saying, okay, in the event of a leak, in the event of a high leak, that people need to get out of the space, what is going to be your plan of action? Are you going to have somebody qualified, or whether or not you're going to hire a third party? So at least you have that kind of that plan of action discussion prior to an event happening. So I guess that would...
Absolutely.
Okay.
Yeah, it's something that needs to... there needs to be a plan in place for dealing with a refrigerant leak. It needs to be really communicated to the personnel that could potentially be responding to it. And really, you could bring it as far back as building it into the system design. So understanding what an owner's intent is on how they want to deal with a leak, should there be one, mm-hmm. and if their intent is to address it with personnel that are on site, ensure that the appropriate PPE is made available to that staff.
Okay. So now, getting into the installation of it, I mean, obviously, we've designed the perfect system. Now it's construction time. Let the contractors do what they will. What are some of the things that you see going wrong with the installation of your equipment?
Well, one of the biggest ones that we've run into is the materials that are used. So we have devices that are intended to be mounted with the conduit coming from the bottom, and the reason for that is that we don't want any condensate kind of gathering and dripping down onto circuit boards through the conduit. Water damage is one of those things that's never covered under warranty. So by having the conduit come up from the bottom, you eliminate that risk, at least from dripping on the board. Use of unshielded wire is another one where certain contractors have tried to save a little bit of money or make use of wire that they may have already had on site, and using unshielded wire certainly can contribute to noise issues, which can manifest into nuisance and false alarms. So
those are typically the biggest two.
Those are the big two. I mean, always, we've enjoyed a lot of loyalty in the contractor community, where contractors who have worked with our systems tend to be repeat buyers, mm-hmm. so they become quite comfortable with them. But really reading the manual, taking the time to read the manual and understand how these devices are intended to be installed is really the single best preventative step that can be taken to ensure the system works as intended. I mean, there are so many differences moving from one manufacturer system to another that it's really almost a crucial step to ensuring that it's going to work right when the power gets turned on.
Mm-hmm. Now, as far as when these systems actually get turned on, obviously with construction going on and the coordination or wiring being required, is there an issue, or I mean, it seems kind of self-sufficient to say, well, if you want safety, you should have it from the beginning when you're going to start the chiller, right, or whenever you're going to load up the chiller. If you're going to have vehicles or anything like that, to have it as early as possible. I mean, is there, I guess, any other standard as to when you should have these active?
Well, I would agree with you. The sooner the better at a real general level. Now there are some gotchas that come along with that. Now we've recently seen an example where a system was installed right away, and then they've gone back and painted the space after the system was installed. We've seen people install systems and then seal the floors and those type of things can really play havoc with gas detection systems. Obviously, from a sensor perspective, the electrochemical cells all include a diffusion barrier. So things like paint or sprayed-on coatings, once they're airborne, can stick to that diffusion barrier and prevent gas from actually flowing into the sensor cell. Mm-hmm. When we're talking about solid-state sensors, it can be much worse because a lot of those coatings can continue to off-gas for months, and that sensor oftentimes will not be able to tell the difference between an off-gas from floor sealant or carbon monoxide. I recall seeing an example of a condo building in Minnesota where they sealed the floor after installing solid-state sensors and effectively ran the heated garage all through the winter with 100% heat all the time.
Wow!
Because the sensors thought they were seeing gas all the time.
So I guess another reason to get away from that solid-state sensor.
Yeah, I mean it's one of the ones that really highlighted it for us that if you don't need to use this technology, there my view is that there are better technologies available for the same cost. So why would you not go down that road?
Right, and especially when you talk about construction, I think you've just named two things: painting and floor sealing. Those are going to be like the last things that are done. So, I mean, if you're going to start the system anytime before that, you're going to have to go through those two phases. So
yeah, and it's if there's steps that can be taken to protect them during that process, then if they need to be installed prior to, I mean, there's certainly you talked about a variety of different reasons why you would want them in place and active as early as possible. Oftentimes most times during the construction stage, these parking garages are workplaces, and as such, we have a duty to ensure that the occupants are protected. An easy way to do that is to turn on the gas detection system, but you do need to be mindful of what's going to happen after that could potentially interfere with its proper operation.
Okay, now I'm just talking off the top of my head here because when I think about construction and I think about air handling units, typically you're going to have your construction filters, and then you're going to change those out and you're going to put the final filters in before you leave. I mean, would it make any sense to say during construction you're going to have the sensors active, to protect the construction workers, and then afterwards you change those, as a last step, you go in and you change those out. I mean, have you ever seen that done? Is that cost effective, or is that even possible?
Well, I haven't seen it done from a commercial perspective. What we have seen is that on some of our products there is effectively a protective sticker over top of the face of some of the sensor modules that can be removed after. It does inhibit gas flow a little bit, but it does allow the system to work. In other applications, more industrial applications, we actually have clients who will ask for a second set of sensor filters, and so they'll keep the first one on while they're doing all their assembly, painting and finishing of their product, and then they'll replace the filter that may have been hit with overspray or something with a new one before it's shipped to their client.
Okay. Now those filters you're talking about, is that for a particular type of sensor, or is that?
In this particular case, it's an activated charcoal filter.
Okay.
That's used on a combustible sensor.
Okay.
But certainly there are. Should a client really want to go down that road, that we can provide tearaway filters, tearaway stickers, effectively that will still allow some gas flow,
mm-hmm.
but will protect the really the finish of the sensor from marring prior to occupancy of the space.
Okay, so probably best is to cover it up when you're doing those final finishes, but
exactly,
it's one of those coordination issues that need to be handled with the contractor. So,
yeah.
talking about maintenance, now that we've got them in, and construction is done, what are we talking about maintenance here? I mean, what do we need to do as far as, testing these things and making sure they work, and periodic testing, or changing out things, or what do we have here?
Well, really, the requirement for testing is one that in many cases is codified and is actually part of health and safety, whether it's state or provincial law. The requirement to verify proper operation of these systems. What I can tell you is that the more often that they're checked and calibrated, the safer they're going to be. And in many cases, the more energy efficient they're going to be by ensuring that a system is only activating at the design threshold. You prevent early activation, so unnecessary ventilation, which can occur and can be quite costly. So it's really the requirement for maintenance is, from our perspective, we recommend an annual, a minimum annual calibration. Mm-hmm. Really, a 6-month check, a twice annual verification of operation is always a good idea. One of the issues that we can run into with certain sensing technologies is that when the sensor does die, and that's the system or the component of the system that really has the lifetime associated with it. Mm-hmm. When a sensor does die, it can sit at a zero output level, which effectively looks like no gas. Mm-hmm. It's simply not responding anymore. So there very well could be gas there. And by doing that verification a couple times a year, you ensure that that's not a case on the site you're working on. So it's an important safety check.
So that's a calibrated gas that you're kind of just spraying on the sensor to see that it detects, correct?
Yeah, in most cases. Now, where that gets a little bit tricky, and as I spoke about a little bit earlier, with solid state sensors, they require ambient temperature and humidity levels to respond properly. So, flowing gas from a pre-mixed cylinder. Mm-hmm. Oftentimes will not give the most accurate calibration because it's 100% dry coming out of those cylinders. So one of the tricks that's often used in the industry is to run it through a wet sponge or a humidifier of some sort so that it does pick up some humidity, and that can work, but it's not really the best way to do it. The best way, and the way that we promote at Armstrong, is to have that sensor in a mixing chamber where you're creating that target gas concentration using a mixture of ambient air and pure target gas, and you're tuning the sensor to that environmental condition. It's certainly more intensive of a process, and it's one of the other reasons, especially in commercial environments, that we try to steer people away from solid state sensors.
Okay. So now, I mean, I guess with lifetime longevity, you're talking about the sensor being more or less the weakest link in the system. What sort of lifespan are we looking at from an owner's perspective?
Well, it's going to again depend on the application, and
Mm-hmm.
it's going to depend on the sensing technology. From a electrochemical cell, dealing with vehicle exhaust, typical lifetime for CO sensors is between 3 and 5 years. Armstrong Monitoring warranties all of our commercial CO sensors for 3 years. So we're expecting people to get anywhere from, in reality, 4 to 6 years of usable life out of them. From an NO2 perspective, the original NO2 sensors that a lot of companies were using, you'd get about a year to 24 months out of them, and now we're starting to see sensors that are getting into 3 and 4 years. so the technology is really improving, and it's extending sensor life. Infrared sensors will be somewhere between 5 to 10 years. Catalytic sensors typically 3 to 5 years, and solid state actually have really about the longest life expectancy, somewhere between 7 to 10 years, which is one of the reasons they were so attractive.
Okay, so I mean, essentially, depending on what type of sensor you have, you're going to be looking at anywhere from typically the 3 to 5 year range.
Yeah, and that's kind of a good rule of thumb to work from.
All right, Scott. Well, we have a lot of great information here. We talked for quite a while, but I think it's all good and some great learning information, obviously, and with safety being of foremost importance here. So, if anybody wanted to learn, if they didn't get everything they wanted out of this episode, where's some of the places they could go to learn a little bit more?
Well, probably our best resource is our website, armstrongmonitoring.com. Lots of information on not only our systems, but applications, hazards in those given applications, and strategies for dealing with specific target gases. They can also reach us by email, sales@armstrongmonitoring.com, or by phone at 800-465-5777. For those listeners who may be in the U.S. Or Canada, we're very lucky to have what I consider one of the very best rep networks in the industry, and we can certainly channel anybody over to one of our local reps that serve them in their area.
Excellent. Well, for those listeners, we'll make sure we get that information posted in the show notes, so you can have it there. You don't have to write it down while you're driving or running. So, I appreciate you being on the show, Scott, and thank you for your time.
Well, thanks very much for the opportunity, Matt.
All right, and we're back. Thanks once again for Scott to take the time out of his busy schedule to be able to talk with us. We got a lot of good information there. It's amazing. I look at the clock and I'm like, wow, this is running on close to an hour. But I think that there's a lot of good information in the show, and I hope you got a lot out of it. So if you did, feel free, pass it along. Let us know. I mean, like me and Scott were talking, it's about. If we can save somebody one headache during the construction process or the design process, it's well worth spending the time here to talk about something that seems so simple, but is so often just kind of mishandled. Between who specifies it, who buys it, who installs it. Is the mechanical contractor buying it? Is the electrical contractor installing it? What's the temperature controls contractor supposed to do? Is it supposed to be on normal emergency power? It's just, there's so many things to think about when you think about these types of systems. So I really appreciate Scott and his, network of people being able to, help us out on times like this. And don't, if you have a question, don't be afraid to ask. Talk to somebody who is, a little bit more knowledgeable about installing these things. But hopefully you are now that person. And if you like what you heard, please share it. If you want to have any other different kinds of topics, please let me know. We're getting requests in, so you can contact me, matt@buildingx.co, or just visit the site and shoot me a message there at buildingx.co. Otherwise, we will wrap it up this week, and we will talk to you later. So until next time, remember, know what you build, and share what you know.